have a look at this idea of stability we introduced in the class the other day. We asked some key questions like, why is the tower leaning? We had some good suggestions there in terms of things like an earthquake was suggested by someone, because they were aware that in earthquakes you get subsidence of building because liquid and the finer silt layers actually come to the surface, and you don't get the proper support into the building, so they do lean over at places like Christchurch and so on. Some suggested it was weak foundations on one side in the design of the building or when it was first put together, and someone else suggested that it was to do with the actual bedrock underneath not being stable or solid enough, and that's the one I think it is actually down to. So that was a good idea there. Why hasn't it fallen over at the moment? Obviously it hasn't leant far enough over for it to actually become unstable enough to actually topple. So this introduced the idea of when will it actually topple. And it's not a question of what time it will topple there, the when. It's a question of how far will it lean before it actually falls over there, and it just can't hold up any longer. So I guess you need to then consider, when do objects actually topple over? When does this situation occur? So we did get some shapes out to sort of show that, and we tried some cylinder shapes there. People also had a cone shape that was like this. They also tried one this way around, and they also had it left on the side there to see what that sort of did. So there were different size cylinders as well, different heights, and they talked about which one was more stable, and so they actually tipped them over until they did topple over and saw what the situation was like. Someone suggested there was a centre of gravity of these objects, and that was important. They knew they had to push it over so far before it fell over, and people realised that in the cube's case it would be right in the middle of the centre of gravity. In the case of the cylinder, you could still go right in the middle, and they tried tipping it over certain degrees there, so they would try rotating this over like that. And basically, as long as the centre of gravity stayed above that support base there, this one here, this is your support base area here, as long as it stayed above that and didn't go outside it, then the object would fall back there if you let it go. So it wouldn't actually topple over as such. But if you tip it further, actually try rotating it just a little further like that so it goes outside the support base, so the support base there. So if you tip past there, the centre of gravity would no longer be above the support base there, and in that case, it would actually continue over and topple. So that was the case with all those sort of ones. So what was key then was the taller ones actually tended to fall over easier without too much of an angle needed, because the centre of gravity was quite high, and it turned out you didn't have to tip it very far in terms of an angle before it actually went past that support base at the bottom. So centre of gravity being high seems to not be a great idea. In the case of the cone ones here, there was actually already an X marked on one of these shapes here, and the X was closer towards the base of the actual cone than the top of the cone. And the reason for that being the centre of gravity was moved down because you've got a wider section of mass down here in this area, and there's less mass up in this top area, so the centre of gravity shift down towards the bottom where the actual object's a bit fatter or wider. So just bear that in mind as well. That one was quite hard to topple over in this position. Here it was quite hard to keep it staying up, in fact almost impossible, with that centre of gravity being very high. And the reason for that was here you've got a nice big support base, okay, with a fairly low centre of gravity, so you've got to tip this a fair way. So in this case here, you need to actually sort of tip this a fair way there. Oh, I've lost part of my course. You have to tip this a fair way there before the actual centre of gravity there, just there, was no longer above the support base. So this is almost above it at the moment there, just about ready to tilt. So, but that's a fairly big angle you've tipped it through to get it close to the tipping. Whereas you look at the next one over, this one here, check the one there out, that one does not require much of a tilt there before the centre of gravity actually moves above that little narrow support base. So the problem here you've got is that the centre of gravity is very high, and you also get a very tiny support base there. It's a very tiny one here. So it's something to sort of consider. It's the size of the support base there, as well as how high the centre of gravity is. Okay. If you bear this in mind, going back to the Leaning Tower of Pisa problem here then, we were considering that the Leaning Tower of Pisa is actually pretty low then. It's probably even lower than that. Okay? And at the moment it's clearly above its support base here, and the support base is actually slightly bigger than that because it's got a little step that goes around the bottom of it. Okay, so when you look at what could be done to actually stop the tower from falling over, then this one here, people suggested that you could actually add some concrete around the bottom of this. Okay, to increase the size of the support base, so they build bigger. It also would lower the centre of gravity, bring that centre of gravity down, making it harder to topple. Okay. Other suggestions in the class were to actually put a pole of some sort on the side here, like struts or something, to actually support it, but that would lose that sort of aesthetic quality and make the mystery of why hasn't fallen over yet, and that sort of awe-inspiring look of it would be poorer. So in the end, what they did definitely do is they actually had a crane in position back in around 1998, and they were adding lead weights to one side here to lower that centre of gravity and move it down to one direction to increase the stability of the thing. And it's been fairly stable ever since at that same angle. So this idea of stability becomes important. Lots of things. If you're looking at wrestlers, why do they squat down and why do they spread their feet apart? Well, there's two impacts of that. One would be that they're spreading their feet further apart would make the actual the support base larger. So if their feet were fairly close together here like that, and they were just standing more upright, there's your support base there. It's encompassed by the feet and the area between the 2 feet. You've drawn lines behind them. And if you embed your knees and set into it and go like that, you can actually just slightly increase that support base there so it's a bit wider. But the other thing it does is it actually brings your centre of gravity of your body further down, because here your centre of gravity will be sort of in there, around the belly button actually, normally is. And in the case of this other lower one here, whereas in the case of the person who's squatting down like that with their knees bent, the centre of gravity will actually be lowered down here and drop down closer to the floor there, if you actually go and measure the height there. So you will actually find that centre of gravity will just got down a little bit there from where it initially was in terms of the height above the ground. That height there will actually be different, it will be lower. So again, they'll have to be pushed over further to topple them. Now, last question here, doesn't matter where the furniture is loaded onto a truck as it goes around the corner or it goes around a bend. So you can see this example that I've got here with this lorry here going on, that this is about to fall over and have a crash there. And the reason for that is because it's got a very high centre of gravity. It's right up here somewhere, and if it goes around the corner too fast and gets outside that support base, it is going to topple over and not recover, and that one may still survive it. So you do consider this with buses as well, by the way. If you do have a bus that's sort of going around a corner there, or a truck that's going around a corner, if that's your truck there, and it was a moving truck, for example, there's the wheels there, the tyres. If you did make the mistake of putting most of the heavy stuff and the high stuff on one side inside the truck, like wardrobes and fridges and stuff like that, and it was all stacked on one side and quite high, your overall centre of gravity would be quite much to one side and reasonably high off the ground. And that would mean if that went outside that support base for some reason, it would actually topple over, and you could see that would be a possibility. In the light of that, when they look at testing double-decker buses in United Kingdom there, this sort of design here, they have to make sure that in the worst situation where virtually everyone's gone and actually lined up on the top there because they're tourists and they want to see out the window around London and stuff, for a fully loaded top deck, just how well can you tilt this bus before it actually falls over and the centre of gravity is not above the support base. And they do actually tilt the buses before they leave the factory and test that result to see it actually be safe enough. Some key things to be aware of then for our discussions is the centre of mass is the actual average position of the mass in the object. So it should be the point where there's an equal amount of matter in one set of directions, front and back. Side to side there should be an equal set of amount of matter in both of those directions, and also up and down. The centre of gravity then will be that same position on Earth. So if you've got an object here on Earth with a centre of mass, it should have the same position as centre of gravity. There are some exceptions to that when you start to look at planets, and that it becomes more complicated. Now, the reason we want to know about centre of gravity is the one we just talked about in terms of toppling, first of all. Objects only topple when the centre of gravity is no longer above the support base. That's when they topple, okay, like in the case of the truck here. And there's 3 types of situations that they describe in the book on this. It's called types of equilibrium. So if it's in stable equilibrium, you need to actually raise the centre of gravity here for it to topple over. So in the case of this cone here, it's in a very stable position at the moment with the centre of gravity like that, and it's the right way around. Because you need to lift that centre of gravity up before you can topple this object. So it's very stable, that one there, and quite hard to get the topple over. In an unstable one, the centre of gravity will naturally move lower for any movement. So if you can picture this one here, in any direction the centre of gravity gets pulled down. If you start to topple the actual cone, so this is unstable equilibrium, it's just going to fall down because the centre of gravity is going to go lower. So that's considered unstable. Okay, and you can see it's very hard to make this stable then and actually sort of keep it balanced, because the area of contact here, the support base, is very small. The centre of gravity is very high. It's very hard to keep one directly above the other. And on top of that, any movement will actually pull it down by gravity. So it's very unstable. You can also get one in neutral equilibrium, where the actual centre of gravity stays the same height here for any movement. So if you were to roll that cone around, it would stay the same height. So that's described as being in neutral equilibrium when the centre of gravity is not going up or down. Now the other use of centre of gravity, there's quite a few there, but just bear in mind that it's the centre of gravity that follows a straight line and follows the law of inertia. The other parts in this spanner, if you were to sling it across the desk there and spin it as it goes, you can see that one part, so the head of the hammer here, is going to go like that, so I've spanner my hammer, and it's going to go like this. So that's not really following the law of inertia, but the centre of gravity of the spanner here will actually follow the straight line, straight way through to the end. Okay? And so it's centre of gravity that actually follows that sort of law. Things will rotate evenly if the centre of gravity matches the location of the axle. So if you think of a spin dryer with clothes, ideally you want the centre of gravity of the spin dryer tub with all the clothes inside it to be in the middle where the axle is placed. If it's off to one side, the centre of gravity not where the axle is, you're going to find you're going to get an unequal torque there and weight distribution, and it will actually change its rotation rate and start to wobble as it tries to spin around that axle. And so you'll actually get a wobbling of the machine or a vibration, you'll hear that, so you need to redistribute it. In actual fact, that idea also gives us clues into stars, which stars actually have planets going around them in a likely solar system out in space, because if you see a star wobbling, it's because it's actually sort of not rotating evenly on its centre of gravity, the axle is not anyway, and that's because the planet's going around the thing, or the star, and actually shifting that centre of gravity all the time, so it's not matching its axis it's trying to rotate on. And that's how you can tell whether there's another solar system out there. You look for wobbles in the stars.